And yeah. Thank you very much for this opportunity to present my part of my PhD work here. So my name is Hongliang Wang, and I'm working in the University of Durham with Jeroen van Heulen and Graham Pearson. And so the title is like the thermomechanical erosion of the subcontinental lithosphere by plume-induced mantle flow. And yeah, so the story starts with the cycle of the lithosphere. So we know that, as we know, the cyclic lithosphere can be known from the seismic topography, which is current cycles of lithosphere, and also we can know the cycles of lithosphere from the paleogeotherm, so from the generous data, and then if you compare two of them, if you found a significant difference, like this research shows, 50 kilometers, 50 kilometers difference. So there must be something happen to cause the removal of lithosphere. And so there are two mechanisms about, the first one is mantle plume impact. So the plume rises up and it can erode the thick lithosphere little by little. And then second is metasomatic refertilization. So if the chemical position of the root has been changed, so the buoyancy could lose and the rheology can be weakened. So, So yes, so there is some background about the plume-continent interaction. So in this area in South Africa, so we know that there might be some super plume underneath the lower mantle, and there might be small plumes in the upper mantle. And yes, so we focus on our research on these areas called the Cloetingh and surrounding area. So this seismic image of the superplume. So yeah. And the question is, can this mantle plume impact cause a significant removal of the Cloetingh lithosphere? The answer is no, and hopefully I can convince you in the following few slides. Yeah, so we set up a model like this. So there is a Cloetingh root, thick continent root, and a plume rises up nearby. And this are the thermal initial conditions, the thermal geotherm of Cloetingh lithosphere and geotherm normal lithosphere, and the viscosity structure. And we use a composite rheology in this model. And I won't spend too much time on this setup. If you want to know, and then you can ask. And so here I show one model about how the plume impacts the Cloetingh lithosphere. So the plume rises up left at 30 million years, and then it impacts the Cloetingh root, and followed by the small-scale convection continue to erode the root. So we can see the impact of Cloetingh root is put the Cloetingh root, erode this area. Yeah. And so we do some analysis about this process. So there are mainly two effects of the plume impact. The first is, when the plume rises up and due to the power law, the long-Newtonian rheology, so it can cause viscosity reduce like 2 order magnitude in this area. So this can cause instantaneous removal of this Cloetingh root by the plume flow. And then because the plume is hot, and then it changes the buoyancy of the this area, so it can cause strong small-scale convection, in which will continue to erode the Cloetingh root, like we just saw. Yeah, and yes, and we did 19 models with different Cloetingh root. So the root, we put the root is more viscous by this factor of delta n, and put the Cloetingh in its buoyant root, like 20 kilometers less dense, or 30 kilometers. So this buoyancy buoyancy, and this rheology, strengthening. And we define this delta eta equals 4 and delta rho equals 31 is strong root. So this kind very strong is highly viscous and buoyant. And this one is like intermediately. So it's like delta A equals 3 and delta rho equals 20. And this one is weak, which is a strengthening factor of 2 and buoyancy of 10. Then, so we can see the effect, the plume impact for this strong root. So the erosion of the ground root is very minor, and in this intermediate root, you can see more erosion. And for this weak root, and this another weak root, so in these two cases, actually, the ground root cannot survive for billions of years, and in these two, actually, they can. And so by showing this, we say that the composition-dependent rheology and the buoyancy actually plays an important role in the erosion of root by the plume-induced mantle flow. And in order to show how the effect of the plume effect, and I run a large model to show that there's no plume, and with strong root and intermediate weak root. And what I found is that, if we compare, but this model runs for more than billions of years, so this is 1 billion years. If you compare them together, strong root, and we found actually the erosion of the ground root is not more, and therefore the no plume indication is not more than it's even a bit more than the plume indication. So this means that the long-term erosion of the mantle, small-scale convection in the mantle could possibly already erode the mantle root. So in that case, I run a lot of two models that one has no plume at all, and the other have 3 plumes at 200 million, 300 million, 400 million. And if you compare the quantum root, in this dashed line, this dashed line is a root shape of the quantum root, and this white contour is also the shape of quantum root. And I put this dashed line in this no plume model and put them together to compare them. Actually, you found this model with 3 plumes and with no plume. They have really small difference. So there's no obvious change even made by 3 plumes. So in this, I conclude that the plume effect the mechanical erosion of the plume effect is very small. You need something else. And this actually shows another model with different plume setup. As you can see, so there's this red is reference model, and the blue has more plume flux. It's only in this case that you show a little bit more erosion, but you have like twice the plume flux. So the plume doesn't change too much. And so we apply our model to the South Africa in this Gibbon and Namibia area, so to show in what condition that the significant thinning of the lithosphere in Gibbon area can happen in 70 million years. So we start a model like this. So this is protozoan lithosphere and quantum lithosphere, and this protozoan can be in this model. In model A, have a weak protozoan lithosphere plus a plume impact. In model B, this protozoan lithosphere has a weak root but without plume. And in model C, you have a strong root, but not strong. It's just an intermediate root, as I introduced before, with plume impact. So, but you can see this only in model A that you can see the significant thinning of lithosphere. This dashed line shows the LAB before the plume impact, and the solid line shows the LAB after the plume impact. So there's like 50 kilometers thinning in this area. But in this model and this model, they don't actually have so much thinning. So to explain the significant thinning, the root removal underneath Gibbon, and a plume impact on a weak protozoan lithosphere is required. And so there's some evidence to show that how this weak perizonium could happen. So this could be caused by the refertilization of the root. So if you compare these two root, you can see the refertilization of the crossing root. So this explains how this, okay, this conclusion. So yeah, the plume doesn't change too much. You need something else, like refertilization. Yeah.
Thanks for the presentation. Does the model has a free upper surface? And if so, could you say something about the implications for vertical motions of your models? What do we see as the effect on topography?
Oh, the topography. Yeah, I plot the topography. When the plume rise up, you can see uplift, but like 100 million years later, and then almost disappeared. Yeah.